Okay, looks okay now. Okay. So far in the class, we've been dealing with finite difference discretization, right? What if we had a reservoir that looked like this? We can deal with that with finite differences, but the way we would do it is we would have to basically maybe use a different color. But we'd have to, we're limited to rectangles, right? So that would be the best we could do to conform to the geometry there. Or, maybe we could refine it. Conform a little better. And, eventually, if we continue to refine it, you could have something that tracks that boundary relatively well, but it would take a lot of elements, right? Because remember, each of these is basically, however I'm meshing this is setting the element size, right? So it's going to take a lot of elements to conform to a boundary like that. Or we could mesh it with triangles, right? Now we have no discretization error. We've matched that boundary perfectly, okay? And so let's see how we might go about doing something like this, okay? So this, what we're going to do is called a finite volume discretization. And I think when I derived the equations so that we could talk about interblock transmissibilities and stuff, I called it a finite volume discretization, but ultimately, it's a finite volume discretization on rectangles, which results in the same discretization as a finite difference discretization. We just, calling it the finite volume, as we'll see in a second, allows you to kind of imagine what a flux through a surface would look like, and then you can basically derive how you want your inner element transmissibilities to look, right? And so let's take another look at this. And for this, I know we've been doing multi-phase flow, but since the focus of this is really just on the discretization technique, we're going to go back to single phase flow, just so we can kind of focus on the details of the discretization, all right? So we'll go back and start with the pressure diffusivity equation. Looks like that. I think I derived the weak form. You remember that? And there's a kind of a three-step process to developing the weak form. Basically you move everything to one side of the equation, multiply by a test function, integrate over the body, right? So I'm going to do that again here. And I think most people that would teach you finite differences and finite volumes would not teach it this way, would not go through the trouble of developing a weak form. The reason I do it is really to set the stage for finite elements. And so some of you have had my geomechanics class, and in there we talk about finite elements, right? And in a finite element discretization, you can have arbitrary shaped elements like we have here. Typically we use quads, square bricks or triangles. It depends. Quad just like a four-sided polynomial or a triangle three-sided polynomial. But you can develop other more complicated shapes. But the difference in a finite element discretization is that there's basically a field, right, across the element. There's some interpolated values so that the pressure in an element is not constant, right? It varies throughout the element depending on the order of interpolation. Okay. More importantly, with finite elements, and it's the reason that I introduce it this way, is that finite elements or variational methods have like a really rich mathematical backing. And so if you see that you can cast these finite volume and finite difference discretizations in the context of a finite element discretization, then you can look to the finite element literature, the math literature behind it, which can give you a lot of like stability and convergence proofs, right? How many of you know that? How many of you know what the Navier-Stokes equations are? Right? Everybody. It's like one of the most famous set of equations. Right? Do you know that there's no proof that the Navier-Stokes equations have a unique solution? So everybody who's computing them, which is probably like a few hundred people within 100 yards of us, are computing the solution is something that they don't know that is even unique. That's even in the continuum, right? When you go to the discrete form in some type of finite element discretization, then you introduce all kind of other issues related to the discretization that could lead to non-uniqueness, stability issues, and other things like that. I know it's become popular in the last few years to use finite volume codes like OpenFOAM or some other reservoir simulator, OpenFOAM, CMG, and couple that with geomechanics. Right? Now, if you took my geomechanics class, we had just like 1 day lecture on the so-called inf-soup condition, which is a stability criteria for the BO equations, right? It's not just the BO equations, it's like any kind of so-called mixed field equations that result in saddle point problems, which the BO equations are. So the solution of the BO equation is not a maximum or a minimum, it's a saddle point. And at least in the pressure term. And so I can prove to you via basically just using the tools of functional analysis and mathematics in the context of a variational formulation or a weak form or the finite element method, I can prove to you that coupling a finite volume discretization with geomechanics is not inf-soup stable. It violates the inf-soup condition, which means it is an unstable formulation. Now, does that mean that you're going to always see the instability? Probably not. But in that example, like coupled geomechanics to finite volumes, where it can occur is if you're doing like a fully implicit solve with a very low permeability, like a very kind of undrained condition, you might see what we often see as like checkerboard pressures. So the pressure field across the domain will oscillate like positive and negative values. And whenever you see that, you know that's an instability, and it arises like you can prove it mathematically that it's going to occur. Right? And so this is all kind of an aside, but it's the reason that I kind of like to cast all these problems in the context of the finite element method or variational formulation, because you get this like really rich mathematical backing when you do that, and you can use the tools of variational calculus of variations to prove things about the discretizations that you're using. Okay, so what I'm going to do is kind of in one step, since I already derived it early in the class, I'm just going to in one step move the things to the one side of the equation, multiply by a test function on the left, and integrate over the domain. Right? So I'll have an integral over our domain. I think just to be consistent with what I did earlier in the class, I'm going to say the test function is a function of x, where x is a vector. C, phi, partial p, partial t. Of course, p is a function of x and t, dx minus the integral over the domain w of x like that, okay? Now, what I'm gonna do, so what I'm gonna do is with this term here, the second term, I'm gonna use a mathematical trick, and it's really, the underlying tool that we're using is just integration by parts. But it's in 3D because these are these are vector operations, right? So it's just integration by parts in 3D, and what we'll do with that is shift this derivative, right? This divergence operation, we're going to shift that onto the test function. Okay. So first term remains unchanged. So when you do this integration by parts, a negative sign comes out in the first term, and so that's going to change that negative sign to a positive. And now we have k over mu Then you have a boundary term that's generated here. Like that. All that's equal to 0. Use a little lower one. Okay, this is the so-called weak form, right? The reason we call it the weak form is because up here, right, notice that our pressure field has to have two derivatives. Two derivatives, for this to have a solution, the pressure field must be continuously differentiable, right? Because I got to take two derivatives. Like if k and mu are constants, I can move them outside, and then it's clear like that becomes like a Nambla squared or a Laplacian operator, right? So I get two derivatives. But here, through this trick, we've moved one of the derivatives onto the test function, right? Thereby weakening the continuity requirement of the pressure field. That's why it's called the weak form. Like we've weakened the requirement on pressure, right? So now we just need to have one derivative there. Of course, we need one derivative on our test function too, to have a solution there. All right, and so if I was gonna teach you the finite element method, we're gonna use the finite element method from here. What we would do is basically assume some type of interpolating function or an ansatz for the test function, usually linears. That's where we start, right? And then this would be the starting place for the finite element method. Right? What I'm going to do here, instead of assuming linears, I'm going to assume Wx is a constant, in fact, a special constant that is 1, right? So if I plug in 1 to that equation, then I get all right. To be clear, that second integral is an integral over the boundary of the domain, right? And so basically that would be like a line integral or a surface integral over all the faces of the outer faces of the domain, right? Where n is a unit normal vector emanating from each face, okay? So it's how you define each face. and A would be the area of the face. Okay? So just like we did in finite difference discretization, there's kind of two ways to state this. You can state that you're going to evaluate that first volume integral with a single midpoint integration rule, or you could say that we're just going to assume that Pi, where I is now an element, right? So we're going to break the domain up into elements. So Pi would be the ith element, okay? That's just equal to the average value of the pressure in the ith element. Okay? So with that, all that's just math for saying that the pressure is constant in the element, right? So then, for the ith element, what we would get would be Vi, the first integral becomes Vi C phi, and we're going to use a finite difference discretization for the time, just like we did before, right? So for time, we're going to assume that the pressure is Pn plus 1, where I'm using superscripts for time and subscripts for element indices, okay? So Pn plus 1 minus Pn all over dt, right, delta t. So this is the first integral for the ith element in the discrete form, right? And then for the ith element, we're going to convert that line integral over the boundary into a summation of line integrals over each segment. Or another way to say that is over each face, right? Each face of the element. Right? So this will now be a sum over each face of the ith element. K mu delta P, I'm going to say n plus 1. Depending on how we decide to evaluate P there, it could be n or n plus 1 would give you an explicit or an implicit formulation, right? But for now, we're just going to do it implicit. Why? Stability, right? Linear implicit formulations have unconditional time steps. I can take as large a time step as I want, whereas as an explicit, I have to take tiny time steps. Oh, well, since I've discretized this, that ds or dA becomes the area of the face. Right? All that's equal to 0. Okay. So again, we're just kind of focusing on one element. We'd have one of these equations for every element, right? And then that second term, basically what you have to do then is you have to sum or iterate all over every face of the element, computing that grad p dot n, right? And I mean, probably when you took reservoir engineering, you derived this equation in a fashion like this. You probably drew a control volume, and then you said that mass, the conservation of mass is the accumulation plus whatever's coming in or out of every face, right? That's exactly what this is, right? This is the flux out of every face, in or out of every face, right? So, you might call this Q F, right? So to keep going, we have to decide what to do about the grad P dot n. Right? So we need an approximation for that, for grad P, right, dot n. So if we draw our little domain again, what we're going to do is we're going to compute the centroid of every element. Right? So if the elements are labeled 0, 1, 2, then this would be like C0, C1, C2. And we're going to draw a line segment between those centroids, and we're going to call this D. And what we'll do is we'll call it IJ for in general, right? So basically D IJ is the length of CJ minus CI. Or I guess technically these are vectors, right? Everybody okay with that? So it's just the length of that line segment. And then we're going to use what we call a 2-point flux approximation. And this is pretty standard in reservoir simulation where finite volumes are used. Right? So what that 2-point flux approximation is that grad P dot n of a face is approximately equal to Pj minus Pi, where J and I are the centroids on either side of the face, right, divided by Dij. So again, it's just a discrete derivative, right? It's just an approximation to a discrete derivative. Now, can anybody tell me how good an approximation that is in general? Or maybe another way to state it would be, what's a restriction on what the discretization has to look like in order for that to be an accurate approximation? The dot n might give you a hint.
Each has to have the same area?
No?
Short distance?
No. What if we changed our discretization a little bit? Oops. Same domain. We'll keep that one the same. But what if we did this? I don't know where the centroids are.
Number of fishes?
But if the centroids are like that, and I have a line segment between them like that, the unit normal to that face is more like that, right? The n hat is a unit normal vector to the face, right? To every face. So this 2-point flux approximation is only accurate when you have orthogonal grids, right? Because in an orthogonal grid, my unit normal is exactly in the same direction as the line segment Dij, right? But if you have a little bit of skewness in the discretization, then you have a little bit of error here, okay? Now, so again, this is n hat. Now, turns out that it's still on the, first order convergent because, well, in particular for triangles. Because what happens if you begin to subdivide? Remember when I'm talking about convergence here, remember any numerical solution that we compute only approaches the analytic solution, the real solution to the PDE, in the limit as the elements get smaller, right? So if I take any triangular discretization, I begin to subdivide it. What do you notice happens with those subdivisions? Huh? They become more orthogonal, right? So it's kind of a property of the subdividing triangles, right? So where there's a big error here when the triangle's big, as I begin to subdivide the triangles, then they become more orthogonal. And so the error is reduced. So this 2-point flux approximation is still first order convergent, even with this perhaps little error, right? Okay. Now, we'll talk in a future lecture about, polygonal discretizations that are not triangles. And in that case, you can use something called a multiflux multiflux approximation to get a better, more accurate flux, right? Flux calculation. Okay. So we're going to go with the 2-point flux approximation, and we'll plug it into our equations. So we have VI, C, phi. I'm going to go ahead and put the delta T here for now. Pi n plus 1 minus pi n minus the sum over all faces in the ith element, k mu dij af times p n plus 1 j minus p n plus 1 I equals to 0. Now let's go ahead and multiply the whole equation by 1 over BW. So we get our formation volume factor in there, right? And if you go back and you look at your notes, we called this the accumulation before, right? And we called this, and we called this the transmissibility before, right? And when we write that equation for all I elements, right, then it becomes a matrix system of equations where this is like a diagonal matrix and this is a not necessarily diagonal, but transmissibility matrix. So I could have left off the n plus 1s on the right-hand side and then derived, chose one to be n, or another time chose it to be n plus 1, and re-derived the solution to the discrete equations, or derive the discrete equations, okay? And what we'd see if we did that was you get the exact same discrete equations, right, for the implicit or explicit method as before. Now, the form of the transmissibility matrix will be different, right? Because, for one, you just have 3 sides here versus you had 4 sides on a rectangle, right? But the discrete equations in terms of the discrete matrix equations would be the same, have the same form. The structure of the T matrix would be a little different, okay? But instead of doing that, we're gonna take a different approach that is not needed for this problem, but it's very powerful in more general problems, particularly problems that involve nonlinearities. Okay? And also it's just simpler in my opinion, right? So when we leave the equation in the form that it's written up there, we often call that the residual form of the equation, right? Because we call it residual because you might imagine that if I just guessed the pressures, right? If I just guessed if I just picked 3 values out of thin air for the pressures of my 3 elements and I plugged them in and wrote down 3 equations, right? They wouldn't equal 0, right? They would equal something not 0. And so instead of 0, we're going to call this R for the residual or the out of balance part of the equation, right? The thing that is not 0, but we want to drive it to 0, okay? And so you might write a very generic statement that says this residual, which is a vector because there are I equations, right? In my 3-element example, there's 3 of those equations, right? So R has 3 components. So R, which is a function of P, which is also a vector, right? It's one pressure for every element, equals to 0. That's the equation we want to solve, right? We want to basically use an optimization procedure to figure out how to take any P we guess and drive that equation to 0, right? Who knows a technique for that? Newton's method. Somebody said it. Who said Newton's method? Newton's method. Yeah. So Newton's method is a generic nonlinear solver, right? It's a way to solve nonlinear equations. Now, these equations are not nonlinear, so we don't have to use Newton's method here, okay? Turns out if you have a set of linear equations and you use Newton's method, it will converge in one step, right? What's the normal convergence of Newton's method? Quadratic, right? It's normally quadratic, meaning the error would be the out of balance or the residual term is cut in half every time. So if you have, normally Newton's method will cut the error in half every time, right? And basically you do this in an iterative procedure. In Newton's method, you take multiple iterations, adjusting P each time until you drive it to 0, right? And so the way we do that with Newton's method, maybe I'll see. There we go. So I'll just rewrite R of P equal to 0. This is our goal. And the way you do this with Newton's method is you compute a Jacobian. We'll call it J here. And that's equal to the gradient of the gradient of R with respect to P. And this is a matrix, right? Because R is a vector and P is a vector. So to compute that, if you're familiar with additional notation, that would be Ri Pj, that equals Rij. Maybe I should use different symbols because these are not element numbers. They're components of the vector, right? So let's say R L P M equals J L M. Okay. So we compute this Jacobian, right? And again, we don't have to do this for a linear equation. But when you go to nonlinear equations, to do a fully implicit solve, this is what you have to do. And there's a lot of scenarios in reservoir simulation where you have nonlinear equations, especially when you go to multi-phase flow, right? Because if you have, saturation-dependent relative permeabilities, right? Then you can basically end up in the saturation equation. You end up with a situation where you have nonlinear terms, right? Okay, so then in Newton's method, what we do is we solve the equation J delta P equals to minus R. And we iterate. So every iteration, we solve this equation, and then we update P. I'm going to use a weird symbol, because I've already got so many subscripts. I'll use K to be an iterative, and I'll put it on the other side of the letter. So P at K plus 1 is P at K plus delta P. And you do that every time for multiple iterations, and then you can solve the system of equations. Okay. So, and when we write down the matrix form of the equations, like we did previously, we're basically writing down explicitly what J is, right? It's like T plus B, whatever that term is that when you solve for P in the implicit formulation, we're writing down explicitly. And we can do that for a linear system of equations. The problem is when you have, basically your J is a function of P, right? Then you have to do this iteratively. Now, the reason that and it used to be before, like 15 or 20 years ago, writing down J is very difficult. Sometimes it's called the stiffness matrix or the tangent matrix. It can be very difficult. It could be like pages of derivation and then pages of coding. But how do we do it now? Anybody do some machine learning here? When you solve a neural network, sometimes the word is called backpropagation. What is backpropagation? What is it?
Updating the weights.
How are you updating them?
You have the residuals and then you are using them back.
By doing what? Computing what? Derivatives, right? You're computing the derivative of the residual with respect to the unknown weights and biases. Or pack your unknown weights and biases into a vector P, and you're computing that, right? Where R would be the loss function, right? And typically your loss function is a scalar. So this is a vector, not a tensor or matrix, right? In machine learning, right? Okay, but the actual mechanism for doing that in a computer nowadays is called automatic differentiation, right? AD. And so nowadays when you do machine learning, particularly neural networks, you use a framework. What are they called? Like in Python, what are the common ones? TensorFlow, PyTorch. There's another one, my favorite, JAX. Those are your three dominant Python frameworks for basically computing, automatic differentiation frameworks, right? So basically, and it's part of the reason for me approaching this problem this way, is it's easier to code up, and I get to teach you guys to use a framework to compute gradients of things, and that's very, very useful. Okay. So what we're going to do is we're going to use JAX to compute these derivatives. Okay, and I'll show you an example in just a second. But first, let's just work an example by hand. Okay. So we're doing all the time. So let's imagine that we have R as a function of P, and that results in P0 plus P1 P0 times P1. So that's our residual, and it's vector. Okay? So then the partial of R with respect to P is going to be, right? So we take the derivative of the first equation with respect to P0. What is that? 1. And then we take the derivative of the second term with respect to P0. What is that? P1. So we'll put that there. And then same thing here. We take the derivative of the first term with respect to P1. What is that? 1. And then we take the derivative of the second term with respect to P1, and we get P0. Okay. So now let's evaluate this at a number, or a pair of P's, right? P0, P1. So let's evaluate it at P equal to 2, 3. Right? If we do that, literally just plugging in those numbers, so it's just 1, 3, 1, 2. Okay? So now let's use JAX to do the same operation. Okay. Okay, so first thing I'm going to do, import JAX, and import jax.numpy as j in p. How many of you know NumPy? We've been using it all semester, right? So everybody knows NumPy. The reason I like JAX is because if you know NumPy, you already know JAX. And so JAX is basically, the API for JAX is one-to-one with NumPy. API means Application Programming Interface. So just like you have np.sign, if you want to compute the element-wise sign of a vector, you have jnp sign, but you can also compute the derivative of jnp sign. What's the derivative of sign? Cosine, right? Yeah. So you can compute the derivative of the vector, and it knows that the derivative of the sign is cosine. Right? And all your other your NumPy operations, right? And so that's why we want to use JAX. Now, just like TensorFlow and PyTorch, another thing you get with JAX is you get just-in-time compilation, if you want it, and you also get acceleration on GPUs if you want it, right? So you don't have to use those features, but one thing that means, how Python is really slow in for loops? What that means in JAX is you can write a for loop, just in time compile the function, and you'll get C speed code. You can take your NumPy code, put it in a function, put a just-in-time compilation function decorator on it, and at runtime, the first time you run the code, it will compile that function into something that's going to give you equivalent to C code, and now you don't have to worry about writing for loops in Python anymore. You can do it in JAX. Okay? All right. So what I'm going to do is I'm going to define a function. I'll just use an anonymous function, maybe just to be consistent with the notes. I'll use P instead of X. And I'll call this R, right? So, like, I can evaluate this function, R evaluated at 2, 3, gives me an array as a return, okay? Now, we're not looking to evaluate the function at 2, 3, we're looking to evaluate the derivative of the function at 2, 3, right? So to do that, what I'm gonna do is say dr equals jax dot forward jack r, or maybe it's jack forward, sorry, Jacobian forward r. Now dr evaluated at 2, 3. One, 3, 1, 2. One, 3, 1, 2. So what we can do is basically write our equations in residual form. Literally just write the equation as it looks, code it up just like it looks. The right-hand side, instead of being equal to 0, call it equal to r, where r is a vector, right? There's one entry for every element, right? And then you can use JAX, using exactly what I just showed you, to compute the Jacobian. And then, and of course, in a true nonlinear problem, you have to recompute the Jacobian every time. Right? Here we actually have a linear problem, so you don't have to recompute it every time. You can compute it once up front, right? And then just solve that matrix equation, J delta P equals minus R. Give it an initial guess for delta P on the first time step, and then, or rather, P, right? Choose an initial P, it could be all zeros or all ones or whatever, right? Then solve that equation up there, J times delta P equals minus R for delta P, and then update the old P with the delta P, and then do it again and again and again until you meet some convergence criteria. A good convergence criteria is when the norm of the residual is close to 0, right? That's what you're shooting for. And again, because this is a linear problem, it should just take 1 or maybe 2 steps just because of machine precision error or something. But 1 or 2 steps should be all it takes to converge, right? So nowadays, I never ever write matrix forms of equations, discrete equations anymore. I always just use this. I write the residual form and then use automatic differentiation to compute the Jacobian for me. It's just simpler, way simpler. And then like trying to figure out, which location in the matrix the terms go, right? Think about how we, just as simple as figuring out the structure of that tridiagonal matrix and like figuring out where they go, right? It's tricky, even for a very simple problem. This makes it much simpler, right? So if you looked at J, if you did what I said here on a rectangular discretization and you looked at J, you would see it has the same structure as we did before. Okay, so the last thing, I guess, I probably meant to do this before. is, boundary conditions, right? So this thing I think I called it up there. It's like the flux, right? Q. Okay. So you could replace that term as just with Q, right? And so if you have a domain and you have a Q on the actual boundary, right? So if you have a Q, we'll call it Q0, then basically you just on that face, right? On that face, you just replace that term with Q0, right? So you could think about splitting that summation into faces that are interior and faces that are on the boundary, right? And the faces that are on the boundary, you're not going to have if it's on the boundary, you're not going to have a PJ, right? Because that's outside the domain. So you basically just replace that with Q. Right? For faces in the interior, you don't have to do anything different. You just compute the faces and sum them up. Right? Now, for a constant pressure boundary condition, you're basically going to do exactly what we did before, right? So we're going to assume that we have a ghost cell, right? So the ghost cell can be just a mirror image of the cell that it's adjacent to, right? So if you have a constant pressure boundary condition, then we just assume that we have a ghost cell there. And because we mirror the image, right, the area of the ghost cell is going to be the area of the volume is going to be the volume and the area is going to be the area, right? And so then ultimately what you'll get is just like before, you're going to have like 2 T0 PB in that location of the Q vector, right? So, I don't know how to describe this. Let's say for, if this is the third element, then the third entry in the Q vector would have the 2 T0 PB, just like before. Yeah. So, the procedure for actually solving one of these, right? Then you basically have to, you're going to have some, I'll explain it in the assignment, but you're going to have basically a connectivity array. Let me just draw another picture. All right, so by the way, you could also just this would work if you have a triangle and a square like that. You can have mismatched discretizations. It doesn't really matter. Okay, but so if we say we have element number 1, element 2. Element 3, and then we have node numbers, say 1, 2, 3, 4, 5, okay, then basically we're going to have some type of connectivity array that basically says nodes 1, 2, and 3 are part of element 1, node 3, 2, 5 are part of element 2, and 3, 4, 5 are part of element 3, and then you're just going to cycle through them, right? So your faces are between nodes 1 and 2, right? So that gives you, because you have to compute a cross-sectional area, right? So there'll be some depth into the board, and then the cross-sectional area is just the length across that face times the depth, right? So you have a face between 1 and 2, 2 and 3, and 3 and 1, and you can compute all of those lengths, right? You can also use this information to compute the centroids. Like, you got to know the node positions of 1, 2, and 3. So you'll also have like a nodal array that gives you the node positions, right, in XY coordinates. You know, so I don't know, 0, 0, 1, 0, 1, 1. 2, 1, and 2, 0, something like that, right? So this would be your nodal position array and your connectivity array. And from that, you can basically use the connectivity, right? This, right, if you use that index to index into the node array, that's going to give you 0, 1, then the 2 index. Forgive me, I should have used 0 because it's Python, right? So it should be 0, 1, 3, but sorry about that. But so if you index into the array, right, that will give you that coordinate, that will give you that coordinate, then you can basically just compute the distance between them. That gives you the length multiplied by the depth, that gives you the cross-sectional area that you need to compute the transmissibility. Right? You can also use this to compute centroids, right? So, and compute the centroid and compute the volume, right? So you need the centroid, you need the volume, and you need the length of every face, right? And then with that, you can compute transmissibilities across every face, summing them up, and compute the accumulation as well for that volume. So, you know, you'll have an assignment Tuesday. It'll be well documented. In the sense that, you know, I'll have these arrays already designed for you. You know, they'll already be inputs. You don't have to change or create those. And then there'll just be a couple of functions. Like, essentially, you'll just have to implement the residual function. Right? Everybody okay with it? All right. Finite volume discretizations.